All right, good morning, ladies and gentlemen. I'm going to make you a video here. This is not going to be a version that I did with my 3U, but I'm going to quickly make a video for the lesson on forming ionic compounds. We kind of took a little extra time yesterday to talk about forming the anions, the negative ions, and now this short little PowerPoint. You can see here there's only 9 slides, so we're going to go over this PowerPoint and hopefully we can get caught up a little bit by doing a little video today. All right, so I'm going to go fairly quickly through this. If you need to write the note, which I want you to do, please just pause the video, write the note, and then you can continue on. It doesn't make sense for me to just kind of wait and have you write the note. So formation of ionic compounds is what we want to talk about today. So what is an ionic compound? And let's just bring this up. And you don't have to write this slide down, all right? Don't write this slide down. And again, we got the animations. I'm not a fan of the animations. Whoops, too far. So don't write this slide down. Remember, when we first talked about forming bonds, we talked about forming ionic compounds versus molecular compounds. Remember, ionic compounds, they contain positively charged metal ions, and we know how to draw metal ions, and they contain negatively charged non-metal ions, or the anions, and we know how to draw those now, held together by what we call an ionic bond because they're oppositely charged. So here we've got sodium chloride, metal non-metal, therefore it's ionic, and here we've got something called copper sulfate, metal with a group of non-metals. We call this a polyatomic ion. We'll deal with that a little later on. But because it's a metal with these group of nonmetals, it is also an ionic compound. All right. So let's write down what salts are, or what ionic compound, which we call salts. I'm gonna bring the whole thing in. Again, you can pause, all right, so that you can write this down. So for now, I'm just going to go through it, and then when I'm done, you can pause and write it down. So an ionic compound is formed when we have that metal atom giving its electrons away to the nonmetal atom. We've just completed our lessons on how metal atoms lose electrons to form their ions, and the nonmetal atoms gain electrons. And in the formation of an ionic compound, the electrons that are lost by the metal are then accepted by the nonmetal. Once this transfer happens, it results in oppositely charged cations and anions, and because they're oppositely charged, they clump together and they form a compound. Remember that container of magnets I had the other day, and I said that when a compound forms, it's simply atoms clumping together. Well, when we have oppositely charged ions, they will attract each other due to the law of the law of electrostatics, and they will clump together. This attraction due to the opposite charges we call an ionic bond. All right. Now, in the end, the ionic compound is completely neutral because the electrons lost by the metal equals the electrons gained by the nonmetal, and therefore, when they come together, those opposite charges cancel away, and the compound that we have is electrically neutral. Okay, so let's take a look at some examples here. And again, I'm just going to run through a few of them. Again, it's going to be fairly quick. So pause right now if you'd like to get all set up. Example, sodium and chloride, chemical formula, name. Once you've got that done, then you can continue, and I will continue with the example. Okay, so what we're going to do right now is we're going to do an example of a Lewis, all right, diagram to show you how this is done. So we're going to start with an Na. And if you've got your periodic table handy, which would be awesome, you would see that Na is in group 1, and therefore it has 1 valence electron. And we're going to react that with chlorine. And again, if you've got your periodic table handy, you'll notice that chlorine is in group 17, or 7, right? I like to say 7, so that indicates to us that we will have 7 outer electrons. Okay. So what happens in the formation of this compound? Well, the 1 electron in the sodium is going to be transferred into the position to complete the outer shell of the chlorine, and that's then going to produce two ions. So the Na has now given up its electron. Remember, no electrons left because it's given it away, and that results in a +1 charge. And the chlorine has now accepted that electron, meaning it's going to result in 8 electrons around it, just like we do with all of our negative ions, and it results in -1. And these two things are held together by the attraction of these opposite charges. And this then is the Lewis diagram for the ionic compound, which has the name sodium, because it is a sodium ion, chloride, because this is now a negative chloride ion. So it is sodium chloride, a sodium ion with a chloride ion. Because it takes one sodium and one chlorine to react together, we give it the chemical formula NaCl. We don't write in the ones, but we can imagine that there are ones down here because it took one sodium to react with one chlorine to form one sodium chloride. All right? So that's how we put together our knowledge of our positive ions, the metals, and our negative ions, the nonmetals, to form the chemical compound. Okay. A little definition here. Again, you can pause to write. It's a formula unit. The formula unit is the smallest part of an ionic compound. The formula unit is given by the chemical formula of the ionic compound. All right? Just to contrast, actually, let me see if there's another thing here. Nope. Just to contrast, the formula unit, all right, I'm going to write down FU, don't giggle. The formula unit for our last compound we saw, NaCl, and that is an ionic compound, all right? And if we have something that is not ionic, like molecular, we call it a molecule, all right? A molecule, an example of a molecule would be water, H2O, all right, because it's all nonmetals. And we're going to see that when we draw molecules, that we're going to have lines in between them for the water molecule to draw this. And for the sodium chloride, we don't have lines. We've got that picture that we just did, all right? We've got the positive ion, and we've got the negative ion. So we treat them a little differently. Molecules are connected together, all right, by these bonds, right? They also have some dots on them. So that's a molecule. And a formula unit is an ionic compound, and they have diagrams like this that have the square brackets and the charges. So there's a difference between a molecule, all nonmetals, and a formula unit that's made up of ions. Okay, let's do a few more examples, and then you'll be ready to work on those sheets that you can do here. Let me get this thing out of the way. Okay, so MgO. If we go to our periodic table, again, we can see Mg, whoops, let me get some color here. So this is the title, Lewis diagrams for ionic compounds. Again, you can make a grid, and you can pause the PowerPoint to make that grid. And then I'm going to continue. Okay, so magnesium, going to the periodic table, group 2, 1, 2, 1, 2, 3, 4, 5, 6, right? And again, you can see here that one of those metals can be traded into that spot. This electron, sorry, the metal's electrons can be given to that spot and that spot, and then that's going to result in our ions. So again, Mg, we can treat them as separate ions. We've learned this. It's given up 2 electrons. It's given away its negativity, man, right? 2 negativity. So that means it's going to result in a positive charge +2. So there is that magnesium ion. The oxygen has gained 2. Square brackets, oxygen, 1, 2, 3, 4, 5, 6, 7, 8, and because it's gained 2, it's -2. So there's our Lewis diagram. Don't put a plus in between, they're just stuck together. Notice again, it took 1 magnesium and 1 oxygen, MgO. Metal always first, non-metal second, 1, 1. The name, remember the positive ion, magnesium ion with an oxide ion, magnesium oxide. All right? Let's do another example. Again, magnesium, 2. Fluorine is in group 7 or 17, and you'll check that out. You'll find there's 7. So now notice, fluorine only needs 1, and magnesium needs to get rid of 2. To solve this problem, we will simply use another fluorine atom, because in a chemical reaction, when this compound is being made, there's always lots of atoms around to be used, so we can use as many as we need. So because fluorine needs 1 and magnesium needs to get rid of 2, we will simply use 2 fluorine atoms so that we can accept the 2 magnesium electrons. So what does that get us? Oops, didn't want red. Let's get rid of that red. I wanted red for the transfer. Mg has successfully got rid of its 2 plus 2. Fluorine, and there's 2 of them, F, 1, 2, 3, 4, 5, 6, 7, 8, square brackets. Each fluorine has gained 1, so it's -1, and I need 2 of those. F, 1, 2, 3, 4, 5, 6, 7, 8, and -1. Okay? So this time we needed 2 fluorines, because fluorine could only accept 1, and magnesium needed to get rid of 2. Formula, Mg, 1, we don't write in the 1, F, and this time we needed 2. So we needed 2 of those atoms. What is this called? Magnesium, because it's a magnesium ion, fluoride, because it is a fluoride ion. And we don't put anything in front of here to indicate 2 fluorides. We will worry about that later on. It's just magnesium fluoride. 2 fluorides are needed to bond to 1 magnesium. Okay, one last one, and then I will talk about the assignment, but then I'll finish talking about some properties of these ionic compounds. So lithium. Lithium, when we check, has 1. And nitrogen, when we check, is group 5 or 15. It has 5. All right? Excuse me. So how are we going to make this work? Well, nitrogen needs 3. Lithium only needs to get rid of 1. So in this case, we're going to gather up a few more lithium atoms. We're going to gather up 3 of them. All right, and they each have 1. This dot's for the I, and that dot's for the electron. Let's transfer it over. That's going to take care of that spot. That's going to take care of that spot. That's going to take care of that spot. So that's going to result in 3, oops, don't like the red. It's going to result in 3 lithiums, Li, and they're all positive, 1 plus 1. Sorry about that plus, it's a little ugly. Li plus 1, Li plus 1, and an N that now is full, 1, 2, 3, 4, 5, 6, 7, 8, and -3. All right? So what did we get in this case for the formula? Well, notice we needed 3 lithium, and the metal always goes first. Li3, N, 1. You don't write it in. What types of ions did we use? Non-metal first. Lithium keeps its name, and this is a nitride ion. Okay? So at this point, we now can do the assignment that I was talking about the other day, and it is on Google Classroom, which I don't have open right now. Terrible. I don't have open right now. What are we gonna do? Yeah, I'm gonna go and find this. We're going to, I need to get to the desktop. All right. Yeah, I'm going to escape. I'm going to keep the diagrams. Let's just minimize this. Nope, we're gonna discard them. So they're gone. We'll come back later. And I'm just going to start up Google Classroom. Got to bear with me, folks. Fast forward through this, perhaps. There we go. And it's going to make me log. No, it doesn't make me log in. Nice. So here we got 4C. And I'm going to add the video to the bottom of this when I'm done. And you'll notice here, formation of ionic compounds assignment. There it is. Turn it in for marks. Right, I have it due tomorrow at the end of the day. Let's take a look at that. And so this looks a lot like what we just did just now. So you can see here are the atoms that we're going to work with, okay? Na and S. You can draw in the dots on Na and S and put any extras you need. Here's where you can put the Lewis compound of the ionic compound. That's with them together like we just did a moment ago, right? So if we go back to that, I got rid of the drawings. And formula unit and the name, all right? So you can use that video to do that, all right? And there's the examples there. Notice I've got one big block here again, just like the other day. You can do the pictures on a piece of paper, and then you can take a picture and you can submit it, okay? And you can add it to it. Awesome. Okay, so let me go back now to the PowerPoint for a moment, because I want to now go on and talk a little bit about ionic crystals. All right, you can again pause. And again, I do want you to write this down. It does say recall, but we've wrote it down before, but we're going to write it down again. We talked a little bit about ionic crystals, and I want to talk again about what an ionic crystal is. So when these ions come together to make a crystal, like a little piece of salt, right, that you may deal with. If we jump ahead, here we've got some salt crystals. What happens to the ions is that the ions, because they're all oppositely charged, is they stack up against each other. Here you can see a representation of a sodium chloride crystal. Now I'm going to go back a little bit. The reason I'm going to go back is I want you to write down an example of that on the bottom here. So when you pause, you can write this all down. But I want you to also write down here the fact that the 3D lattice is like Na plus Cl minus, Na plus Cl minus. Because these units will stick together, Cl minus, Na plus, Cl minus, Na plus. And I'm going to do one more row, Na plus, Cl minus, Na plus, Cl minus. Now, remember I talked a little bit about what a formula unit is. There's the word right there, formula unit. The reason we use that term is because there's no way to tell where one piece of the salt begins and ends. Because I can have a sodium chloride right there, but I could have a sodium chloride right there. I could also have a sodium chloride using this group of them right here. So you can see there's many different versions of sodium chloride. There's no way to tell where the one sodium chloride begins and the other sodium chloride ends. And that's different than a molecule like water. With a molecule like water, you can see where the molecule begins and ends. It has a beginning on one end and an end on the other end. And for ionic compounds, you can't see that. That's why we call them formula units instead of molecules. Okay, so we were going to get ready to do a lab today, but we'll do the lab tomorrow. We'll begin with it. And it talks about properties of ionic crystals. And what I'm going to get you to do at the very end is I want you to write down now this properties of ionic crystals, all right? Again, you can pause it. I'm going to talk a little bit about it, and then that'll be the end of my video. The crystal lattice structure of an ionic compound results in the following physical properties of ionic crystals. Because of this repeating structure, and again, you don't have to draw this. You've already got this. Na plus, Cl minus, Na plus, Cl minus, and Cl minus, Na plus, Cl minus, Na plus. What is created here is like a scaffolding. You've probably seen scaffolding on the outside of a building. Scaffolding is what, you put up on the outside of a building if they're fixing it, if they're working on it. And scaffolding is very strong. This is much like scaffolding because in between these ions, these guys are attracted. All these guys are attracted here, which makes a strong little square. But the opposite guys repel each other. They push each other away. And that makes this very strong. If I tried to push on this structure on the side of it, let's say I could somehow take something strong and make a really hard push on the edge of this square would push back. The opposite charges would keep it upright. The attracted charges would keep it from moving. That makes this very strong. Ionic compounds have very strong structures. So what does that do to them? Number one, it makes them really hard. You can't break them easily. You can't squish them between your fingers. You need something hard, like maybe 2 spoons. You could put some salt between them and crush them. They have high melting points. That means you've got to get them really hot in order to break them down. Again, it's strong. They're solids at room temperature. That's because they have high melting points. If the melting point is really high, it's going to make them solids. They do not conduct electricity in the solid state. I'm going to talk more about why that is after we're done the experiment. But they do conduct electricity in the molten state, which is another word for melted state, and in solution. And that's when we dissolve it. Dissolved. All right? Due to the formation of mobile ions. And I will talk in more detail what mobile ions are the next day. Okay? All right. Hopefully that's not too long. Hopefully we can keep your attention through this video. And now you can work on that sheet and get that done. All right? And then we're going to move on with the experiment the next day. All right. We'll see you tomorrow.